What Petitspot tell us about the Lithosphere-Asthenosphere boundary is a third presentation of the CoLiBrI talk series on the lithosphere.
Hello, thank you to join this presentation. This video series is devoted to the process associated to the nature of the lithosphere and its transition to the asthenosphere. Today I will focus on petrological evidence for the presence of small amount of melt at the base of the lithosphere. I will also discuss how melt is delivered to the base of the lithosphere and what is the implication for seismic discontinuity. But before to begin, I would like to thank many contributors, in particular Natsue Abe and Naoto Hirano, without whom this work couldn't have been performed. Most of the information related to the nature of the Lithosphere-Asthenosphere boundary is associated to geophysical evidence. But it's difficult to obtain independent information to test these different alternatives, to explain these geophysical anomalies. Today, I will show you that it's possible to obtain direct information on the presence of melt at the base of the lithosphere by studying Petitspot volcanoes. These volcanoes, which was discovered 20 years before by Japanese researchers on the plate flexure on the Pacific plate in front of Japan. This is very interesting because it's a very small volume of magma, but he was able to rise up to the surface. But before talking about this Petitspot volcano, I will start to explain petrological arguments suggesting the presence of small amount of liquid at the base of the lithosphere.
The Lithosphere-Asthenosphere transition zone is the target of various geophysical studies. Two main distinct interpretations exist for the change in the mantle geophysical property observed at the LAB. Hydratation of olivine crystal associated to a change in the lattice preferred orientation is one of these hypotheses. The second proposes the presence of small degree melts. Kawakatsu and co-author have performed a seismic study on the Pacific plate subducting below Japan to localize the Lithosphere-Asthenosphere boundary. They document a large shear wave velocity reduction at 82 km depths, interpreted as the Lithosphere-Asthenosphere boundary. Kawakatsu et al. Suggest that the seismic velocity reduction in the low velocity zone is associated to partially molten asthenosphere consisting of horizontal melt-rich layer embedded in meltless mantle. Other geophysical studies support this hypothesis. Seismic reflection data from Stern et al. Obtained below New Zealand supports similar interpretation and suggests that the base of the oceanic lithosphere integrates a 10 km thick melt channel. Another argument in favor of the presence of melt is coming from magnetotelluric data obtained in the Central America subduction zone. Neif et al. Image a conductive layer of 15 to 25 km thick at the base of the Coco plate. This conductive layer is consistent with the presence of small degree melts at the top of the asthenosphere. After this different geophysical argument, the question is now, how can we understand the presence of low degree melts at the top of the asthenosphere? The presence of low degree melts at the top of the asthenosphere could be understood by looking at this pressure-temperature diagram for the melting of peridotite. You observe here the mantle adiabat corresponding to the asthenospheric geoterm, and here the dry solidus of peridotite. If you add now the geoterm from the old oceanic plate, you realize that no melt is expected because the geoterm is too low to allow dry peridotite to melt. However, if you add the effect of volatile on peridotite melting, illustrated here by the effect of CO2, it's possible to understand the formation of melts because the presence of volatile reduces the solidus temperature of peridotite by several hundreds of degrees. We observe also that melt composition vary from carbonatite to CO2-rich silicate melts at the top of the asthenosphere. This compositional difference is related to the relative content of CO2 in the melt, as the limit between carbonacetic and CO2-rich melt is fixed to 25 weight% of CO2. If you combine now this graph with the age of the oceanic lithosphere, you could obtain the distribution of melts below oceanic plates as suggested by Mark Hirschman. If you consider the situation at the ridge, the melting is controlled by the mantle adiabat. This suggests that the presence of carbonacetic melts at depths, then the melts evolve to silicate melts at shallower depths. In this situation, melting extends until the base of the crust. In contrast, if you consider the gradient from the old lithosphere, you still find carbonacetic melts at high depths and CO2-rich silicate melts at the top of the asthenosphere. But the melt composition returned to carbonatite in the basalt part of the lithosphere, according to the thermal gradient. This analysis explains the distribution at the LAB of melts as function of the age of the plate. There are two interesting aspects to note in this static model. First, the thermal definition of Lithosphere-Asthenosphere boundary, corresponding to the change from conductive to convective geotherm, do not correspond to the upper limit of melt distribution, but it's located significantly deeper. If you consider the upper limits of melt distribution correspond to the seismic location of the LIB, this suggests that the thermal and the seismic location of the LIB is distinct. Secondly, if you observe the amount of melt predicted in this model, the maximum of melt produced is not at the top of melting zone, but at the transition between the convecting and conductive geotherm. Nevertheless, this figure provides a support to the interpretation for the presence of low-degree melt at the base of the lithosphere, as suggested by Kawakatsu et al. But it is important to remember that this figure assumes an homogeneous distribution of volatile in the mantle. And considering that the convecting mantle contains only 60 ppm of CO2, the amount of silicate melt that you could produce at the base of the lithosphere is extremely low, below 0.1%. This amount seems clearly too low to explain the seismic reduction observed at 80 km depths below the Pacific plate. Even you concentrate melts in lenses as proposed by Kawakatsu et al. To solve this problem, Mark Hirschman suggests that the seismic discontinuity observed at Lithosphere-Asthenosphere Boundary corresponds to the accumulation of melt which have migrated from greater depths, in periphery of mid-ocean ridge, or by upwelling processes. If this idea seems mostly accepted in the literature, this model has some important implications, in particular for the thermal state of the upwelling melts, which needs to be in equilibrium with the asthenospheric mantle first. We will come back on this later. After this introduction, we could return now to the question of Petit Spot volcano. I will show you first that Petit Spot confirmed the presence of low-degree silicate melts at the base of the lithosphere. Then, second, that xenolites and xenocrysts sampled by Petit Spot lava provide evidence for melt migration within the base of the lithosphere and melt addition in periphery of mid-ocean ridges. The discovery of Petit Spot volcanoes was a big scientific surprise. In 1997, during a test drive of the new Keiko submarine, JAMSTEC researchers observed fresh young alkaline basalt on the oceanic slope in front of Japan. The presence of this basalt was unexpected as the presence of young seamounts was not reported in this area. Based on the age of this sample and the current Pacific plate motion, Lausanne was able to estimate the area where this basalt was initially emitted. In 2004, a new crew performed a survey on this region and documented fresh flows and dumps over a large area. The location of petit spot emission was found. In addition to the 3 locations observed in front of Japan, petit spot has been observed in front of Tonga, in front of Chile, and in front of Thunder Arc. 2 other locations are associated to petit spot volcanism. It is the revenated volcanism in Tutuila Island and a series of alkaline seals embedded in radiolorite currently accreted in north of Costa Rica. We believe that many other petit spots exist in front of subduction zone, but the size of this volcano, only a few tens of meters high, make their observation difficult. How petit spots are produced? The location of petit spot, 600 kilometers from the trench, have suggested a connection between plate fracture and the formation of this small cement. In absence of clear evidence for hotspot, Lausanne and co-workers have interpreted petit spot as small intraplate volcanoes produced by the extraction of low-degree melt from the base of the oceanic lithosphere by tectonic process. As illustrated by the schematic figure of Yamato et al., this model suggests the presence of small melt fraction at the base of the lithosphere, and second, in response to extension, the brittle fracture propagates until the base of the lithosphere, allowing melts to be extracted to the surface. Melt at the base of the lithosphere and the extraction of melt by tectonic process are the key parameters for the formation of the so-called petit spot volcanoes. According to this model for petit spot lava formation, we could infer the composition of the melt at the base of the lithosphere by sampling and analyzing lava collected at the seafloor. In this total alkali versus silica diagram, used as a classification for basaltic rocks, I have reported petit spot lava as color symbols, in comparison to oceanic island basalt in gray. You could observe that petit spot lava are alkaline and show a large range of silicate content partially explained by fractional crystallization process. The highly vesicular texture of petit spot lava and glass measurements show also that petit spots melts are rich in volatile, in particular rich in CO2. So this supports the presence of volatile-rich alkaline melts at the base of the lithosphere. But it is not very clear if the composition of petit spot lava at the surface provides direct information of the composition of melt at depths, as the transform through the lithosphere could potentially modify the magma composition. So it is important to understand the extraction mechanism, as it is not very clear if fracture could propagate until the base of the lithosphere, as proposed by Urano and co-workers. To test the hypothesis that deep fracture could open until the base of the lithosphere, we have developed a 2D thermomechanical numerical model. This model, published last year, allowed to understand the lithospheric stresses associated to plate flexure and to constrain the rheological change at Lithosphere-Asthenosphere Boundary. In this model, the lithosphere and asthenosphere are distinct by their respective thermal regime. These simulations show that the viscosity of the mantle is mostly constant from the asthenosphere to the middle of the lithosphere, before a significant increase to the top of the lithosphere. This change in viscosity is associated to a change in the main deformation mechanism, from ductile, associated to dislocation and diffusion creeps at the base of the lithosphere, to elastoplastic deformation for the upper part. As it is impossible to develop brittle fracture in ductile domain, these simulations are against the direct extraction of low-degree melt from the low-velocity zone to explain petit spot formation. These rheological simulations suggest that melts coming from the top of the asthenosphere will percolate first across the ductile parts of the lithosphere until it reached the elastoplastic domain, where fracture may develop. But this model has an important implication for the chemical evolution of melt rising in the lithosphere. If melt rises in the asthenosphere, its temperature is controlled by the mantle adiabat. Now, as noticed by Mackenzie, movement of small melt fraction cannot transport heat, so melt rising in the lithosphere will potentially cool and crystallize. However, it is not very clear which PT trajectory will follow these melts. To test this, we develop a simple model in which melt rise up in dike with different velocity and equilibrate thermally with the surrounding mantle. This model doesn't want to illustrate the mechanism of melt percolation, but just test the effect of thermal diffusion. The following video illustrates the main result. This video illustrates the propagation of a dike of 5 meters across the lithosphere. The first velocity test here is 10 meters per year. You could observe the dike propagation, but you doesn't see any change in temperature, as the temperature in the dike follows the geotherm. Now for a dike rising at 100 meters per year, you could start to see a small delay. This delay in thermal equilibration increases with the velocity, as illustrated here for a dike rising at 1 km per year. It is even more extreme for a dike propagating at 10 km per year, but still the melt into the dike cools progressively. This model shows clearly that the velocity of the melts needs to be extreme to avoid thermal equilibration with the surrounding mantle. Melt velocity is estimated between 2 and 150 meters per year below mid-ocean region. So it is very unlikely that small melts rising into the ductile domain of the lithosphere could avoid cooling, even you consider low viscosity for the rising melt. What is the implication? If you consider a melt rising in the asthenosphere, its temperature is buffered by the mantle adiabat. But when this melt enters to the lithosphere, its temperature will follow the lithospheric geotherm. When a basalt cools, it will crystallize. Experimental constraint indicates that melts will crystallize first anhydrous cumulate. Then, when the temperature reaches the respective stability of phlogopite and amphibole, hydrous cumulate will form. I will show you now evidence for the implication of phlogopite and amphibole in the petrogenesis of petit spot lavas. As shown before, petit spot lava are alkaline in composition, but also share similarity with low silicate alkaline lava from oceanic island, as illustrated in this task diagram. One aspect which distinguishes petit spot lava from typical OIBs are their high and variable potassium-sodium ratio. Potassium-sodium ratio combined with titanium content is a very helpful diagram, because this diagram allows to distinguish experimental melt from peridotite, from garnet pyroxenite, representing or recycling oceanic crust, from melt produced by partial melting of amphibole or phlogopite metasomatic cumulates. Comparison of petit spot lava with a prediction from experimental petrology suggests that either an interaction of peridotite melts with phlogopite pyroxenite melt, or an interaction of melt from peridotite with melt from hornblendite to explain the composition range of petit spot lavas. This clearly supports the implication of hydrous phases in the petrogenesis of petit spot lava, and also indicates the implication of the lithosphere as these phases are only stable at lithospheric temperature. Another argument for the percolation of interaction of low-degree melt within the base of the lithosphere is the composition of mantle xenolites sampled by petitspot lavas. These xenolites show mineral assemblages typical of abyssal peridotite, with the association of olivine, orthopyroxene, and clinopyroxene. But when we measure the trace element content of the clinopyroxene, we observe a very unexpected composition. This diagram reports the composition of clinopyroxene normalized on primitive mantle. Clinopyroxene from depleted peridotite, corresponding to the austenitic lithosphere, fall normally in this gray band. The depletion in very incompatible element is associated to the process linked to the formation of residual peridotite at mid-ocean ridge. The composition of clinopyroxene measured in petitspot xenolites is very distinct, with a depletion of heavy rare earths, suggesting an equilibration in the garnet stability field, and an enrichment in very incompatible elements. Such signature was never reported in austenitic settings, but is frequent in clinopyroxene from melt metasomatized garnet peridotite sampled by kimberlite from Capval Creighton. This signature is interpreted by Gregor et al. As evidence for melt percolation across the cratonic lithosphere. So the composition of petitspot xenolites provide evidence that the base of the austenitic lithosphere was percolated by low-degree melts producing a metasomatic enrichment of the Pacific lithosphere. We have now multiple xenolites showing similar clinopyroxene enrichment. Evidence for melt percolation before the emission of petitspot lava allow us to propose a new model for the formation of petitspot lavas. This model assumes a dynamic interaction between low-degree melts from the low-velocity zone and the lithospheric mantle. As the lithosphere moves in direction of subduction zone, extension at the base of the lithosphere allow low-degree melts to rise up and percolate within the base of the lithosphere. During this percolation, melt interact with peridotite, cool and crystallize, producing a metasomatic enrichment of the lithospheric mantle and addition of hydrous phases. As this process happens in multi-steps, melt addition eats the base of the lithosphere, allowing new melts to rise up progressively. At some point, melt reach ductile brittle transition, allowing hydrous fracture to propagate, allowing melts to be extracted to the surface, producing petitspot volcanoes. One interesting aspect we need to take into account here is the fact that the composition of petitspot emitted at the surface doesn't correspond to the composition of low-degree melts, but correspond to the interaction of these low-degree melts with metasomatized lithosphere.
At this stage, you probably ask yourself, okay, Sébastien, petitspot volcanoes are interesting. But what is the implication for Lithosphere-Asthenosphere boundary?
If you remember, a key question about the Lithosphere-Asthenosphere boundary is how melt is delivered to the top of the asthenosphere. The formation of petitspot and the presence of metasomatized xenolites demonstrate not only that melt could rise up in the asthenosphere, but also that these melts could percolate across the base of the lithosphere. And this is, for me, an important change in the way you could interpret the asthenosphere-lithosphere transition zone. Now, if you take the real seismic data on the anomaly observed in the Pacific plate, you could observe that this anomaly doesn't follow the isotherm, and most of them are located in the relatively cool region of the lithosphere. How can we reconcile the thermal structure of the Lithosphere-Asthenosphere boundary with the location of the seismic anomaly? If you consider the hypothesis that low-degree melts rise up, when this melt enters to the lithosphere, this melt will percolate, cool, and interact with surrounding peridotite. Experimental petrology allows to predict the evolution of melt. When melts reach 1100 degrees C, we will have the formation of amphibole-bearing peridotite, while at 950 degrees residual melt crystallize, producing carbonated minerals such as magnesite or dolomite. On the right, you could see the extent of amphibole-bearing peridotite field. This field encloses some of the seismic anomaly observed below the Pacific plate. But we observe also that many anomalies seem inconsistent with the percolation of melts coming from deep. As indicated by various authors, the addition of deep melt to the low-velocity zone is not the unique mechanism to explain the formation of seismic anomaly. Another hypothesis is the addition of melt in periphery of mid-ocean ridges. This mechanism of refertilization of the oceanic lithosphere is supported by numerical simulation from Keller et al. For melt and volatile extraction at mid-ocean ridges. These models show that a large proportion of melt produced in periphery of the ridge is not collected to ridge axis, but is added to the lithospheric mantle as the plates spread away from the ridge. I will show you now that garnet xenocryst observed in petit spot lava provide direct evidence for such mechanism. Garnet are quite rare in oceanic settings. So when we found the garnet xenocryst in one thin section from petit spot lava, we were very excited. The specific composition of this garnet allowed us to demonstrate that this garnet is not coming from peridotite, but have a metamorphic origin. This diagram, Mg number versus chrome content, allowed to distinguish garnet composition observed in different types of lithology. The garnet xenocryst observed in petit spot lava show chrome content too low to come from peridotite. In contrast, this garnet xenocryst seems to own to the garnet pyroxenite and eclogite fields, which contain magmatic cumulates and metamorphic rocks. Our garnet xenocryst show rare earth pattern typical for garnet observed in eclogite xenolites, indicated in this diagram by these gray lines. Such composition, in particular the flat middle to heavy rare earths, support an origin associated to the metamorphic transformation of a mafic protolite containing plagioclase. Eclogite observed in cratonic lithosphere is interpreted at high pressure metamorphic rocks from subducting mafic lithology, which is added to the cratonic lithospheric mantle. In our case, it is unlikely that our garnet xenocryst found in the middle of the Pacific plate come from the subduction oceanic crust, as no process seems able to add such lithology to the Pacific plate. In contrast, we suggest that this garnet forms by subsolidus cooling of a gabbroic cumulate trapped at the base of the lithosphere. This schematic model illustrates our hypothesis. First, melt escapes the focusing mechanism at mid-ocean ridge and percolate and cool within the base of the lithosphere. According to experimental constraints, such melt will produce a gabbroic cumulate containing olivine, clinopyroxene, orthopyroxene, and plagioclase. When the plates spread away, the gabbroic cumulates cool progressively, and garnet is formed by metamorphic reaction from plagioclase and orthopyroxene. The important point to note here is that the reaction happened only if the pressure is over 0.7 GPa. So the initial gabbroic cumulate do not form at the base of the crust, but it's really within the lithospheric mantle. Interestingly, the estimated pressure for the gabbroic cumulates formation is consistent with the location of off-axis melts predicted by Keller et al. Simulation. We conclude that refertilization of the oceanic lithosphere in periphery of mid-ocean ridge is a realistic process. The question is now, can liquid trap at the base of the lithosphere explain some of the seismic anomaly observed in the Pacific plate? If you put the melt distribution produced in periphery of ridge in the global context of oceanic plate evolution, you realize that melt present close to the ridge will necessarily cool as the plates start to be older. To predict the phase assemblages that you produce during this cooling, and then to calculate the potential seismic effect, we use the melt distribution predicted by Keller et al. And combine this with petrological constraints. But to make such prediction, we need several assumptions. The first one is how melt is distributed within peridotite. Simulation of Keller et al. Suggests that melt could represent more than 10% in volume at the base of the lithosphere. So, melt could be distributed at grain boundary, but also as melt pockets or veins, as observed in several mantle outcrops. But in both cases, you produce metasomatized peridotite. The distribution of melt within peridotite plays a role in the type of lithology you will form by cooling. If you consider melt at grain boundary, you will produce cryptic and modal metasomatism, and we could use experimental constraint on peridotite plus water to predict the formation of amphibole-bearing peridotite plus carbonate minerals at low pressure. In contrast, if you consider that melt evolves in veins, you could predict the formation of anhydrous cumulate at high temperature and hydrous cumulates when the temperature reaches amphibole stability. You could transfer this constraint in this diagram for the thermal evolution of the lithosphere. In both cases, you will produce metasomatic effect. In the following part, we will use the constraint on metasomatic veins, as such configuration have more chance to produce seismic effect. To calculate this effect, we use the distribution of melt provided by Tobias Keller. For each point of the model, we calculate the Petit trajectory using the isotherm calculated with the plate model from Stein and Stein. After 60 million years of cooling, a large part of the melts located initially around 50 km depth is transformed to amphibole, while melts are now restricted to the lower part of the lithosphere. We focus in particular to the generation of amphibole because this phase could have a significant effect on seismic velocity. To calculate the seismic reduction associated to amphibole, we use the values calculated by Rader et al. These figures show that 20% of amphibole could produce more than 3% of shear wave velocity reduction. If you look now to our prediction, you observe that the presence of amphibole cumulate could produce seismic reduction around 1 to 3% as function of the initial proportion of melt. The seismic reduction associated to the presence of melt is more difficult to calculate, because the distribution of melt in sphere or as layer could play a fundamental role to explain seismic reduction, as illustrated by this figure from Lee et al. For our calculation, we assume an intermediate conversion model. Our prediction suggests that small seismic reduction is associated to the presence of melts, not because melts have no effect, but mostly because the amount of melt predicted in our model at depths over 60 km is very small. Now, if you combine the seismic effect of amphibole and melts, you could observe the evolution through time of seismic anomaly produced by the cooling of melt trapped at the base of the lithosphere. Our analysis suggests that after 20 million years of cooling, you have a strong seismic anomaly associated to the cumulated effect of residual melt and the presence of amphibole in metasomatic veins. This effect decreases with time, as illustrated in these different panels. You could see a separation of the effect of amphibole at the top and melts at the bottom of the melting column reported here. If you compare now our prediction with the location of seismic anomaly observed in the Pacific plate, you see an interesting correlation. Our model suggests that seismic anomaly observed at mostly constant depths in the Pacific lithosphere could be linked to metasomatic cumulate, including amphiballs, while deeper anomaly could be associated to melts. But of course, this interpretation needs to be tested more in detail in the future. As a petrologist, what is clear for me that it is unlikely that seismic anomaly observed below 900 degrees C isotherm could be explained by the presence of melts. The temperature is too low to stabilize melts. Even such melts are rich in CO2. This is because CO2 will react with peridotite and form carbonate minerals. The presence of hydrous cumulate produced in peripheral ridge is a potential explanation. The addition of melts from below is also a possibility, but it is important to remember that if melts rise up from the asthenosphere, it will cool and crystallize when entering into the base of the lithosphere. We arrive now at the end of this presentation. I will just summarize the main point that I developed in this video. Low-degree melts may exist at the base of the lithosphere, but only if volatile are present. The maximum content of melt is expected at the thermal LAB, which is 30 km deeper than the top of seismic anomaly observed in oceanic plate. If melt rise and percolate within the base of the lithosphere, this melt will necessarily cool, evolve, and produce metasomatic cumulate and volatile-rich differentiated liquids. All this information suggests that the low-velocity zone may correspond to a transition zone with low-degree melt at the top of the asthenosphere, evolving to the metasomatic cumulate, including various proportions of volatile-rich differentiated melt in the base of the lithosphere, as illustrated in this figure. Considering the seismic anomaly observed in the Pacific plate, we suggest that this anomaly, interpreted as a LAB, may represent the formation of metasomatic cumulate associated to the melt addition in periphery of mid-ocean ridge, or may be associated to melt migration within the base of the lithosphere. Thank you very much to have followed this presentation, and take care of you.